Got it. Okay. After the unnecessary technical challenges of the morning, good morning, and welcome to the second morning lecture. Today, I will introduce some of the special boxes that are used to write down quantum mechanics and quantum computing, and I'm going to give you some rules that give them meaning, just diagrammatic, so that allow you to do diagrammatic reasoning with these boxes without necessarily referring to the quantum process or to the linear map that the boxes represent. So yesterday I talked about how diagrams are used to reason abstractly. I said there are various theories that you can interpret them in, and today I'm going to start giving you building blocks for the quantum side of things, so actual quantum processes. Now, the basic process in these lectures, I will write my diagrams left to right. So I'm going to take the same notation as quantum circuits because I'm going to mostly use quantum circuit examples or things like that. But you can, again, draw bottom to top. You can draw top to bottom. Whatever convention suits your needs really is okay. The motivating example for today's block is rotations of a qubit, really. So let's take a qubit, which is a point on a sphere. And the state of a qubit, to be precise, is a point represented by a point on the block sphere. Let's take 0 at the top, 1 at the bottom. And the things that you can do to this qubit correspond exactly to the ways that you can rotate this sphere. So if you want to rotate the qubit in the z basis, you rotate it about the z-axis. There's x rotations, which are about the x-axis. Y rotations are about the y-axis. So there's really just those generate all possible rotations, by the way. So it's enough to have 2 of those, as long as you allow arbitrary angles in your rotation. Let's start with x rotations. X rotations are rotations about the, z rotations. Z rotations are rotations about the z-axis. So you can imagine that there is an axis that goes through 0 and 1, all the way through the sphere, and you are rotating about that axis by, say, some angle alpha. And I will represent the rotation, a z rotation, by a circle. It has 1 qubit coming in, 1 qubit coming out. So this is a transformation. Something comes from the left, goes into the qubit. So just to remember from yesterday, in and out, like that. And I will annotate the angle of the rotation. I'll just write it under. And typically there's going to be no confusion because I will either use Greek letters or I will use multiples of pi, which are legitimate angles, but typically not really numbers that you see like scalars or in phases. It's not very common to see a phase of like 1/√pi or something like that, or 1/pi. Anyway, this is going to be the notation for the z rotations. So these are z rotations. And I can adopt a similar notation for rotations about the x-axis. So rotations about the x-axis take the x-axis as their fixed axis of the block sphere. And they rotate about the circle orthogonal to that axis. So the equator for the x-axis. It's really the same, but flipped. And so the x rotation by alpha would be something like this. So I will denote these rotations by a similar notation. And instead of having an empty dot, I'm going to have a dot with a cross on it. And again, these are x rotations. Yeah, sorry, you have a question? Now, these rotations by themselves, there's not much that I have to do other than observe that if I have any one of them and I do a second rotation about the same axis, so say about the z-axis again, by a different angle, say beta, the angles add up. And similarly, if I do 2 rotations about the x-axis one after the other by alpha, then beta, that is the same as a single rotation by alpha plus beta. And that's, so far, I hope, fairly straightforward. So 2 rotations, same as 1 composite rotation. Now I want to represent this fact by some diagrammatic rule that I can use while I reason about circuits to know, for example, that if I see a Z rotation by some angle and then another Z rotation immediately after, then these two add up in some way. So I can fuse them. Okay? And so I introduce a fusion rule. And I say, well, okay, so I have a rotation by alpha followed by a rotation by beta on the same axis. And I picked Z and X because they are special. They have a relationship that will help us reason about them, really. What I get is a single rotation, so I can fuse them. I imagine that these two are little blobs of blobby matter that I can squish together, and the angles add up. So I have one blob with alpha, one blob with beta, and they become one blob with alpha plus beta. So I motivate physically, or with reference to qubits, I motivate this kind of diagrammatic rule. And now I don't really have to think about these as rotations anymore, or I kind of have to if I want to do more things, but for rotation's sake only, all I need to know is that when I see 2 of them, they sort of add together. And that addition is just a rule of rotations composing in sequence. I don't know what they do when they meet. So when there's an X rotation and a Z rotation, that I don't yet know what to do. But when they are the same on the same axis, I know that they compose this way. And now I take the same rule and I observe that the same exact holds for the X rotations. Again, if I have an X rotation followed by an X rotation, it gives me an X rotation with the sum of the angles. Now this motivates a rule called as fusion, or it motivates a simple example of a more powerful rule called fusion. So let's give another example. I'm going to take the same setup. In fact, I'm going to start with the first slide. And I'm going to say, actually, I don't just care about the rotations here. I also want to be able to represent states. For example, I want to have some notation to represent the 0 state, or some notation to represent the plus state or the minus state, states that I care about, states that are simple to prepare or simple to understand. And so I say, I'm going to use something similar, and maybe this will help me while reasoning, to represent the state by an angle of alpha around the equator. Is going to be a dot. Again, a state is something which goes from nothing in to something, or a qubit in this case, out. States are the recipe to prepare something on a wire. A wire carries information. It says there's a qubit here. There's a qubit in some state here. And the state is the recipe that tells you, if you don't know anything, how do you produce something in this wire? What is the thing in the wire? Like, how do you describe it? So states are recipes, and the state on the left would be something like 0 plus e to the I alpha 1. And I'm not going to normalize it. So it's going to have it's not going to be a normalized state, because it is convenient to work with this kind of spiders without the normalization. I will then at some point tell you I omitted normalization factors in a lot of places, and I will explain to you why it doesn't really matter, because you omit them across the entire spectrum of possibilities. So all you have to do is sum all the probabilities and use that to normalize the outcomes of your measurements, and that's it. So that's not a particularly, it's not a problem, but it helps at the start to not have to carry around numbers across your diagrams. You might just forget what the right numbers are. So the state on the left is this state on the equator, and the state on the right is going to be a state on the X equator. So it's going to be a state around here, which can be written similarly, except I swap 0 with plus and 1 with minus. And it's, again, this a state that I might care about. So these were plus and minus. Those are left fixed by X rotations, but these states are states on the equator. And the point of defining, so just to be clear, this state here is called little dot with one leg out and angle alpha. That's, from now on, that is going to be the name of that state. And this little state on the left, its name is going to be little empty dot with alpha and one leg out. So that's the new name that we give to these states. And these are special, of course. They're not all possible states of a qubit because there are only two circles. But it turns out that between these states and the rotations that we're allowed to apply to them, we'll be able to write arbitrary states of the qubit very shortly. But before we do so, why did I use this notation? Like, why did I decide that the same notation that I use for the rotations, innocent enough, is also a good notation to use for the states? And in particular, why is it that I picked states such as plus and minus? So this would be plus, this would be minus, yes. And you get that plus is the empty dot with no angle, minus is the empty dot with a pi angle. And on the other hand, I have 0 and 1 here, and 0 is the cross dot with no angle, and 1 is the cross dot with a pi angle. And you might wonder, why is it that the Z basis states, 0 and 1, are represented with a cross dot when the Z rotations are represented with an empty dot? It seems like I have swapped my notations, but this is not about the basis of the rotation. This is about the circles. So you have to focus your attention on the circles, squint a little, and imagine that the same dot rotates the states on that circle. So I'm now going to show you that if you take the same exact fusion rule that I introduced before to talk about the rotations, and instead of applying it to two rotations, you apply it to the initial states that I had, magically, I again get the right result, because I start with a state that has here an angle alpha. I apply a Z rotation to it. It gets rotated by a further angle beta, and so it becomes a state this time with angle alpha plus beta. So the reason why I picked those color combinations is because really I care about the way that the rotations act on my states, not about where the states are. So this is a crossed with alpha, and this is a crossed spider state with alpha plus beta. So let me just rewrite that. So this notation was chosen so that the same rule, the same fusion rule that I wrote down for rotations, also tells you how to compose rotations and certain initial states. Not all of them, but certain initial states. And now that you have some initial states, you can write all of them. So just to show you that this is enough, take any point on the sphere, on the block sphere, use effectively spherical coordinates, and say I start from 0, a common convention in quantum computing anyway. So this is applicable directly. And I have to, in order to reach any point on this, any target state on the block sphere, I have to do two things. I have to first go down to the right latitude and then rotate around the right longitude. And maybe a way to do this would be to sort of go down this between the meridian across plus and 0. That's perhaps one way to do it, but that's fairly common. So do a Y rotation, but Y rotations are a bit weird, so I'll try to avoid them. And instead, I will do X rotations and Z rotations together. So I could go down to the right latitude and then sort of go around. But instead of going down this meridian, I will go down the X equator to the right latitude. So I'm going to do a theta rotation by X, and then I'm going to do some phi rotation by Z, and I'm going to get my state. So my state, any general state, can always be written as start from 0. Remember the crossed spider with no angle. So this is 0. Then apply X rotation by theta, and then apply a Z rotation by phi. But now we already know that this recipe that I gave is slightly too complicated. There's already an opportunity to simplify things, at least from the diagram's perspective. Yes, most of quantum computing starts from 0, so maybe you do want to start from 0. But if you have a diagram and you're just trying to reason about it, then why not observe that the initial state and the first rotation are the same color? And we perform our first simplification practically. And we say, actually, there is no need to start from 0 at all. You can start from this theta state along the axis directly. So I can start from here. I can write this state here. And then from there, I can rotate. So it really takes only 2 of these blobs to write an arbitrary state on the block sphere. And that's the general state. And of course, you can also write it the other way, starting from an equator state and going up. So it's there's going to be a rule that tells you which ones commute, but that's going to come later. So now I will observe something. I'll observe more things. There are more examples of these operations that kind of have to do with being the same color. I've given you rotations. Those sound fun enough. I will now give you some arithmetic, which is going to be binary arithmetic, of course. So I will observe that there is 0 and 1. So I have definitely 2 bits, sorry, 1 bit, the 2 values of 1 bit. So I can imagine that 0 and 1, and really they do correspond to these states, okay? And now I want to do sort of basic classical Boolean algebra with them. So I want to maybe, what are the classical Boolean operations? And, or, not, XOR. And then there's at least 2 more that you may not really think about. There's XOR, yes, but there's actually copy, because somehow you have to be able to write your variables twice. And typically there's also some kind of delete, because you want to be able to throw away your variables. And you don't have to really think about these in classical logic, because in classical logic, you're free to copy your values as much as you want. But this is quantum theory, and you cannot copy all values. Maybe you can copy some. So we're going to have to introduce some operations that we can use to then construct circuits based on our classical intuition, because a lot of the basic gates that people use come from classical logic. The control NOT gate is a classical logic gate turned quantum. The NOT gate, or the X gate, is a classical logic gate turned quantum. So we start with the classical logic ones, and then we get some, maybe we get some more. So let's start with, in fact, this is equal to. Let's start with, there's going to be a copy operation of some sort. So I'm going to write operation with 2 legs in, sorry, 1 qubit comes in, 2 qubits come out. So this is in, and this is out and out. Okay, and this is going to be a copy. I cannot copy all states, right? You're familiar with this idea that quantum states cannot in general be cloned. So there is no map that will work for all of my states, but I don't care. All I care about is that it copies those 2 states. I just needed to copy my bit values, and everything else, whatever happens, happens. So I'm going to ask that if I plug the 0 state in, then I get 2 copies of the 0 state. And if I plug the 1 state in, then I get 2 copies of the 1 state. Like that. So I ask that it sends 0 to 0, 0, and 1 to 1, 1. Yeah. So I have 1 qubit, and I want to be able to make copies of my states. And now I look at what happens with this copy operation, and I introduce another one. I introduce a delete operation. Let's start with those. They are easy enough. So I don't even know what delete means. Yes.
From intuition, it would be going back to the 0 state. Might be wrong.
Going back to the 0 state would be delete and then prepare something. So yes, that's actually quite good. You want to do whatever the deletion is, and then prepare 0. But I don't care about the preparing 0 again. I just care about being able to remove wires from my circuit. So I just need something which gives me a scalar, it gives me a number. So what number? Well, I don't want to have to carry around unnecessary numbers. So I want this number to be 1. I don't want it to be some phase that gets applied to my circuit. So if I could, and maybe I can't, but I can, turns out, I'd like to have some box which applied to 0 removes everything. So it gives me the empty diagram, which is the scalar 1. And if applied to the state 1, also gives me nothing. I can remove it from my diagram, which is the same as saying that I get a number 1 out of it. So I get an amplitude, the amplitude is 1. Well, you have to really think, I get a complex number, the complex number is 1, because if you think of them as amplitudes, you're kind of thinking that they are part of the components of some state vector. These are not, they're just numbers, okay? Everything that appears without legs on this piece of paper is a number that floats around that you use to do calculations. Some of these numbers are going to be familiar, others are not going to be familiar, but I hope that the numbers 1 and 2 are familiar enough. Yeah, so maybe those we can use. So let's start with these 2 operations. I have introduced two new dots that again looked like the previous one for some reason that you might disagree with. Why should the copy be the same as a z rotation? Why should the delete be the same as a z rotation? So I said I have z rotations, but now I also have these weird, z rotations. I have the states on the equator that are already kind of objectionable in their own right. Then I have this copy and this delete map, and they're all the same kind of dot. And they don't look like the same. Like if you describe these operations, why would they look the same, really? And I think this is one of the great initial benefits of adopting this particular language. Well, this is the ZX calculus or ZX calculus. There are many more pieces in it, so I will then give you a proper overview. But one of the initial advantages is that its notations are chosen in such a way that it is very easy to understand what commutes with what fuses with what. Essentially, it tells you that gates that you might have thought as new or different or weird are made of the same stuff as other gates. And so, for example, you can conclude that if you have a C0 gate and you have a CZ gate and they commute on, and they share their control, then actually you can prove that they commute. So you can prove immediately by fusion, and we'll do that after, that you can push one through the other, even though from the matrices that might not have been entirely obvious. It is obvious from the diagrams because they were drawn with these basic pieces that work well. So the point of this calculus is to give you basic building pieces that are very easy to manipulate, and then you construct gates from them. And the fact that you have few basic pieces helps you reason about which parts of the gates do what. But yes, you had a question. This is a digression. Sorry, where is that? Here you are not really caring about that. You're saying I had 1 qubit, now I have 2 qubits. How that happened in the universe is a mystery. It could be. Let me give you an example. And again, I will redraw this afterwards and prove it to you. But imagine that you're in a quantum computer and you say, I have a qubit that comes in, which could be 0 or 1, but I don't care. I want to copy it. And then I want to make a copy, but I don't know how to make a copy. So what I do is I apply a C0 instead to another qubit. But I fix this other qubit on the 0 state. And I apply a C0. And then I say that the copy, my copy operation, is this larger box. And now I have a box which has 1 qubit in and 2 qubits out, because I chose to forget that I had an ancillary qubit that was fixed to some state. I choose to forget that. That's quite common in quantum computing. There are a lot of operations. You can obviously say, I apply this unitary to these qubits where the first 1024 qubits are set to some interesting value, and the next 2048 qubits are set to 0. That's quite common. Or you can say, I have a process, a box, that takes 1024 qubits and spits out 3096 qubits. Because the other ones, yes, it's true that I could set them to 0, but I can also set them to some other states and internally modify my implementation, and the result is the same. So you sort of you can, by having different numbers of legs in and out, you can decide which pieces of information you want to focus on. You want to look at your circuit and say, I care about this part. This is my input, and the rest is inside, and I don't care. And then how you compile that, keyword, compilation, how you make that into a sequence of instructions that your machine understands, that's for a compiler to do. And we don't really have to care about that. Compiler, yeah, if you want to, this is a field that's really young. We don't have the C compiler, okay? It's not, we're not in a world where it's obvious how to compile this code. It is highly non-obvious, and we have machines that work completely differently. The quantum computers are exotic, all of them. There is, even the ones that appear to have the same technology don't have the same underlying hardware. Like the Google machines and the IBM machines, you read about them, they're superconducting qubits. Yay, probably they're the same. No, very much not. They're not the same. They are slightly different pieces of superconducting silicon, and they have different native gates. So when you compile a circuit, I will write my nice circuit with my CNOTs and my gates, rotations, and then I compile it to one or the other. I have to pick completely different sets of basis gates to compile into. So the question is for compiler optimization. And in this time, you can go into compiler optimization. It's a very fascinating field for quantum computing. But for the purposes of quantum information, which is what we are doing here, I'm going to say I only focus on the relevant information, and I imagine that I can create new qubits, or I can even remove qubits from space. It's just that I don't want to see them. But yeah, it's an excellent point. So let's go back to, in fact, let me check that I have, yeah, my volume is up, so I can hear if someone online asks questions. So these are some basic building blocks. This is a rotation, part Z. This is a equatorial state. This is a copy, and it's a Z copy, and this is a Z delete. What are the rules of copying and deleting something? I know, I mean, this is like Boolean algebra 0, because you typically don't even care about what it means to copy multiple times. It's kind of obvious, but here it isn't. It's not going to be. So if I take a single state at the start, some bit B, and I perform one copy, I get 2 copies of that bit state B. And then I take one of these legs and I copy it again. What happens? How many copies do I have? The answer is simple. So if you go with it, you get points. Okay, the answer was simple enough. 3 copies. And does it matter whether I copy the second one or I copy the first one? It doesn't, because it's the same. I'm actually imagining that this is copying some bit of information, so it's really the same. I get a new equation that tells me that copy is associative or co-associative, to be precise. I make one copy, then I make a second copy, I make it on the left, I make it on the right. It doesn't matter, because it's the same exact thing I'm copying on both sides. So I just get 3 copies. It doesn't really matter how I do it. So that's one equation that I didn't really know about yet. That's something new. Maybe I have to add it to my calculus. In fact, it turns out it's probably good if I add it to my calculus in some form. Otherwise, I don't know how to deal with multiple copies. And I can say, okay, great. Since I can do as many copies as I want, and the order doesn't really matter, all I have to do is to make my notation a bit lighter, is to define a big industrial strength copy. That copies things m times, and it's defined to do a copy, then a second copy, then a total of, how many copies are there? -1, because you get 1 extra from the first one. So the first one gives you 2, and then the right leg continues to, actually every one gives you a left leg, if you will, and then the right copy also gives you a right leg. So you get m-1 copies, give you m states in the out. And it doesn't really matter how you do this tree, okay? Well, any binary tree that you can write, however you want to arrange it, you can arrange it the other way, and it gives the same exact result. So however you arrange it, as long as you have 1 leg coming in and m legs coming out, and it consists of these dots, then you will get your copies, because you're just making the copies in some order. And there are very many of these, right? How many binary trees are there? Quite a lot. I don't need the answer to the question. There are quite a lot of ways of writing a binary tree with m leaves, a balanced or unbalanced binary tree. And all of those give you exactly the same copy. So these are many equations, which starts getting interesting. How do you identify all of these? But even more, how do I deal with deletion, right? What happens if I take a copy and then I delete one leg? So I start with a state, one of these computational basis states. They get copied. It gets copied twice. And then one of them goes to 1. I'm left with the other one. So it's the same as doing the identity. It's the same as doing this. Right? So copy and delete. I mean, delete should in some way interact with the copy. It should cancel out. And the same with the other side. So if I make a copy and then I throw away with this weird state, with this weird whatever it is, I throw away one of the two legs, then I have nothing. And that's kind of interesting, because that big dot has one leg coming in and 0 legs coming out. So really, I'm just removing legs by doing some kind of fusion. Yeah, both of these operations are a form of fusion, because if you look at them, you imagine you start with a double copy, and then you fuse these two things together, and you get a fused big blob. Yeah, something like that. It looks more like a cow to me, but it's fine. And then it wobbles back to its size. And if you do a deletion, it's exactly the same, but it happens that the second blob had no legs, which was sad for the second blob. So you take the same picture. Come on. And you just remove the legs of one side. You get a blob with one fewer leg. Something like that. Yeah, so this gives me the inspiration to define something new. So first, I'll tell you what these two new maps are in terms of qubits. This map here, in terms of Dirac notation, in case you're interested, it's the map that sends 0 to 0, 0, and 1. I'm going to have to use a different color for the maps too, because bracket is confusing. And 1 to 1. So it can be written as I sum over the bits, 0 and 1. I get a bit in input, and I spit out twice 2 copies of that bit in out. So that's my map. And now it turns out I can also write this one. It has to be a map that sends 0 to the number 1 and 1 to the number 1. So it's a row vector, because it has to be something which sends a column vector to a number. So it's a row vector. Which row vector is it? Well, I just gave you the 2 components. So it is this row vector. What is that? Well, that is the plus bra, but it's not normalized. So really it's √2 times the plus bra. Because the plus bra would have been this one, would have been 1 over √2, 1 over √2. But there are reasons why I don't want to carry normalization factors, so I made this unnormalized. And yeah, my delete blob, this delete spider, is just the plus bra. It's a bra for the plus state. So just reverse it, and it happens to delete the computational basis, but not everything. And so I define a new building block, and I say, actually, I have spiders. So I generalize this completely. I had something with 2 legs in and 1 leg in and 2 legs out, 1 leg in and many legs out. I have something with no legs in and 1 leg out, something with 1 leg in and 1 leg out. I have something with 1 leg in and no legs out. So clearly the number of legs at the left and at the right kind of can change, can vary. And I will just define a general notation for this. And I'm going to call it a spider. And it's going to be one of these blobs. It will have n legs in, and it will have m legs out. So it's n on this side and m on this side. And I am going to give it an arbitrary phase. And I'm going to say this is your one of the two new basic building blocks that you will use. Thou shall use this as a building block for all your quantum needs. And this is called the Z spider. And you can write it generically. It's not hard. You just take all the bit strings. You take n bit strings on the left. You take, actually, I should probably do m by n. Oh, who cares? You take m bit strings on the right, and you have to consume the n qubits on the left. You have to produce the m qubits on the right, and in the middle you have to maybe do something. So what is going to be the scalar that's associated to those? It's going to be e to the I alpha. In fact, I don't want to take all bit strings. I want it to be so that it copies. So far it has, don't write it down yet because I'm going to erase it. I don't want it to have all possible bit combinations. I want them to be special because I want 0 to go to 0, 0. I want 0 to go to 0, 0, 0, 0, 0. So actually, these are not all bit strings. They're just some bit strings. And in fact, there are so few of them that they can be written with a single index. It's B in 0, 1. And I will just repeat my B many, many times. So it's B dot 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 B here, and it's B dot 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 B here. So for example, it's 0, 0, 0, 0, 0, e to the I alpha 0, 0, 0, 0. And I don't want this phase to be, constant because otherwise I can pull it out. I want this phase to only appear on one of them and not the other. Otherwise, this wouldn't be a rotation. So really, I have to simplify this and write it as e to the I p alpha. So it's going to be 1 when they're all 0, and it's going to be e to the I alpha when they're all 1, something like that. So you can rewrite it a bit more explicitly if you want as 0, 0, 0, 0, 0, 0 plus e to the I alpha 1, 1, 1, 1, 1, 1. So it's as a linear map, it has very low rank. It kills almost everything. It keeps 1 qubit worth of thing. It's sort of all the qubits that come in. The only states that are preserved are either all zeros or all ones. Everything else gets thrown to 0. And then whatever that bit is, it gets copied, it gets multiplexed m times, and a phase is applied to it conditionally. And that is the most general thing that you can do. And this gives you the copy, it gives you the delete, it gives you the rotations, it gives you everything. This is a very general building block. And now I play the same exact game. And I say I have a Z spider. And I have, so I'm going to give you a reference slide for it. I'm going to draw them big because, I don't know, actually, let me not be too confusing. The size doesn't matter, just in case it was a point of wonder. So I have some Z spiders. I have some X spiders. I just do this by changing bases, okay? So I don't even have to think about what the meaning of these X spiders are, or what the meaning of these X spiders is, sorry. I will just do it by mimicking the ones in the Z bases, but doing it in the X bases. So I'm gonna say this one is 0, 0, 0, 0 plus e to the I alpha 1, 1, 1, 1. So that was the definition for this spider. Whatever that means. We saw that it was useful. It had some special cases, could be used to do copying, deleting, could be used to prepare some states on a circle, could be used to do rotation. So it's multi-purpose. There are many more, obviously. And then I will take the other version and I'm going to make it exactly the same. In fact, I'm going to make it so exactly the same that I'll copy paste it. Copy paste. I'll just change all the zeros to pluses and all the ones to minuses because it's in the X basis now. And this is going to be plus dot 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 plus, plus dot 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 plus, minus dot 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 minus, minus dot 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 minus. This is a different spider that I get. I don't know why it's useful though. What does it do? Well, some things I already know, because all I did was swap between Z and X. So if I change colors across the entirety of my pictures, I'm going to start getting some results that I didn't kind of expect, perhaps. So I learned, well, I knew that Z rotations compose with states, right? And I knew that for the same happens for X rotations. So this is alpha plus beta. This is alpha plus beta. See, all I did was change color. I just swapped the colors of all the nodes. So by color, I will mean either empty or crossed, because I decided to not use green and red for number one, speed, and number two, I imagine most of you don't carry around a pencil case with a green pencil and a red pencil. Neither do I. So I want to have a notation that maybe looks a bit more drab, but I can write with a single pen. So that's why I picked this particular notation. It also reminds me of the quantum circuit one. But ZX, all I did was swap colors. And now I can learn new things. So for example, I knew that if I had B pi, where B is in 0 or 1, and I copied it, I got two copies of B pi of this classical basis state, which was either 0 or 1. Good. Now I take that equation and I change all colors. So I rewrite it, but the state on the left becomes a Z state. So one of these Z equator states. The copy spider becomes a spider in the X basis, and the two copies are again on the Z equator. So I learned something new. Just by the intuition that perhaps my rules should be invariant under flipping colors, because really I just changed basis from between one and the other. So I just flip between X and Z. Technically, I will have applied a Hadamard. That's what happens here, but we'll get to the rule later. For now, just imagine whenever you see a rule, swap all colors from X to Z and Z to X, you get a new rule that is also valid. And so now we learned that we have a new copy map and that we have a new delete map. So again, this was B pi, and I could delete it, and I got the number 1, or the empty diagram, denoted by this dashed box. And on the other side, I learned that if I take one of these equatorial states, which are going to be plus or minus, and I delete it with the crossed spider with no legs out, so the X spider with no legs out, I also get the empty diagram. So I now have a new copy map, a new delete map, new rotation maps. I have them in the X basis, I have them in the Z basis. So I have more ingredients. And I observed that the rules, there are some rules that govern, that involve spiders of different colors. Those for now I don't care about. But there are all these rules that I wrote that involve spiders of the same color and kind of look like fusing blobs together. And this is the first rule I will write down in general, and it's called the fusion rule. So the spider fusion rule is one of the basic building blocks of this formalism. It says that if you have two spiders of the same color with two angles alpha and beta, they have some input legs, they have some output legs, maybe 0, okay? It doesn't matter. So a bunch of them. And they have at least one leg between them. So this is at greater than or equal to 1 leg between, okay? So they have to touch. They have to be connected. If they are connected, then you can take them and fuse them into a single spider. You add the two angles. You take all the legs in input, they go into the same spider. All the legs in output, they go into the same spider. So if you started with N1, N2, M1, M2 legs, then on the right, you're going to have N1 plus N2 legs in, M1 plus M2 legs out. Just to be clear, like the number of legs that are attached to the boundary must be preserved, because you have to imagine this entire thing as a single big box. The signature, the things that come in and the things that come out can't disappear, because these are equal, right? If they're equal, they have to mean the same thing. Certainly, you cannot have particles that pop out or disappear in the process. So that's preserved. What changes is the number of legs in between. You go from 2 spiders to 1 spider. And now you take the same exact picture and you repeat it for the other spider, and you get the same spider rule, but for the X spiders. Maybe I should remove this for now. So I take the same rule, and again, all I have to do is change colors, and I get a new rule. These rules are called fusion. So this is spider fusion. Okay, so for now, though, I have I've shown you that there's a duality between the 2 bases. I can go from one to the other, and it seems a bit pointless, perhaps, because yes, okay, I can copy the Z states, I can copy the X states, great. They do interact, but not really, because all I know is that I can take the spiders of one color and copy them, spider states of one color and copy them through the other color, but that's about it. I can't really do any computation yet, right? I've done basic. I was so basic in my rules of Boolean algebra that I've given you 0 Boolean operations. None of them yet. And I'll give you at least 1, so to get things started. And I tell you that this spider that you introduced by just changing color now has some use. So if I take an X spider with 2 legs in and 1 leg out, and I ask, what happens if I apply it to these Z basis states? What happens if I apply it to a state which is either 0 or pi? So let's write it as A pi, and a state which is B pi. That is the Z basis. Yeah, yeah. So these are the states either 0 or 1. See, this is the state B in the Z basis. Correct. It's right. So this is B, and this is the state A, where A and B are in 0 or 1. So yeah, that's the Z basis. What happens if I apply one of these X spiders to the Z basis? You already know, actually. I don't have to already tell you. You can already do the calculation. What does the previous slide say? What happens when 2 spiders of the same color touch? They fuse. And what happens to the angles on them? They add. So I now have 3 spiders of the same color that touch. What happens? They fuse. How many legs do I have in overall? 0. How many legs do I have out overall? 1. So let's start with that. Nothing in, 1 out. So I get a state. Which state? What happens to the angles? They add up. So I write A pi plus B pi, but pi, 2 pi is 0, right? So really, what is that? It's A XOR B pi. So the angles of the states gave me bits, and the fusion gives me binary XOR. So this map is the XOR on the Z basis, to be precise. It's XOR on the Z basis. So I now get a new operation. And in fact, I already knew that its unit was one of these spiders. And indeed, the XOR is a monoid, right? So I have all the rules of a monoid. What is a monoid? It's a binary operation that has a unit, left and right, is associative, and in this case, it's also commutative. So I have, by fusion, I get all of these rules. I get that it has a bilateral unit. I get that it is associative, because again, this is fusion. I don't even have to add a rule for associativity. I don't need it. All I have to do is fuse it into a single blob with 3 legs in, and then unfuse it the other way. When I said all of these 3s, they're all equal, how do we make sure that they're all equal? This is wow. You just fuse them into one big blob and then unfuse them in whatever order you want. And that gives you all the equations that you need. So there are many equations that come from the spider fusion rule. You get like quite a lot of them, even for a small number of spiders. So this is, and then it also happens that all of these spiders are commutative. So I can change the order of the legs. But they don't have to be, as in there are good examples of generalized spiders that are not commutative. So people typically write things like, they say that commutativity is sort of like take any number of legs and then focus on two of them and then say that these two legs can be swapped between them. I don't know if that industrial scale picture is necessarily super helpful, but I'm going to put it in for the sake of reference to other work. So if you read works on the ZX calculus, because this is what the ZX calculus is, you're going to see sometimes that it starts with the big spider law and it puts some twisted legs. And what they mean is you can permute any pair of legs and there is no difference in the result because these are XOR is a commutative operation. The order of the operands doesn't matter. Copy is a commutative operation. All the copies come out the same, so it doesn't matter again. So now I have building blocks that allow me to do some stuff already. And so I start asking, what can I do that's interesting? The first thing that I want to do is to look at the Bell state. So how do you construct the Bell state? How do you get the Bell state? Because I said the Bell state is the cup. Right? I told you the cup of wire is the Bell state, and then someone, I don't remember who, asked, how do I know that this is the Bell state? And the answer is obviously you don't yet know, but you will soon today know that that's the case. So first, one observation, and the observation is that if I have a rotation by 0, what is it? What does the rotation by 0 do? Nothing. So I can just remove rotations by 0. Both of them. Just a rotation, okay? So one leg in, one leg out, you can remove it. Other ones are not rotations. A copy is not a rotation. A plus state is not a rotation. If you have one leg in and one leg out and no angle, then there is this rule that tells you that you can remove the spider. So these are the identity spiders. And now I want to do the calculation that produces the Bell state for me. And in order to do so, I need some kind of 2-qubit operation that I don't yet have. I will not introduce notation for a 2-qubit operation. I will manufacture one out of the building blocks that I already have. And it's going to be the C0. So I'm going to show to you that this thing here is the C0 gate, affectionately named. Why did I draw it with a leg in between that's horizontal? That seems a bit weird and maybe a little cheeky. It is partly as a reference to the fact that you get some kind of Feynman diagrams that do something like, sorry, let me make a new slide for it so I can then continue. So look at this and imagine that you have qubits coming in, 2 qubits coming out, and the virtual qubit in between. That's actually the right way to think about it. If you think of these as tensors, you're contracting along a qubit that you never see. It's a qubit that doesn't exist, but it's 1 qubit worth of information. Okay, it's the same as saying, well, it's almost the same as saying, and Gerardo will forgive me for the metaphor. It's almost the same as saying that you have 2 electrons coming in, 2 electrons coming out, and they interact through a photon, through an exchange of a virtual photon. And much as the direction of the virtual photon doesn't matter, the direction, and this is not equal, but it is kind of like the same thing. The direction of the virtual qubit doesn't matter. As in, it turns out that I can write these by first doing a copy and then doing XOR, or I can write it by first doing a copy in the other basis and XOR in the other basis, if you will, and these are the same. It happens that this is the case for qubits. 4 qubits. But if you then want to do quantum mechanics with this formalism, which you might as well want to, and you want to use, instead of the Z basis, the position basis, instead of the X basis, the momentum basis, for an arbitrary, maybe the reals or maybe the circle group or the integers. You work in some lattice, some discrete lattice. You want to have a lattice group. All of those, all good. There, this is no longer true. There, these two maps are not the same. One is the inverse of the other, so things still work well, but there the order matters. But for qubits, which is the setting that we care about here, and in quantum computing, it is kind of nice that you don't have to remember the order of the legs. In fact, you never have to, you really only have to remember connectivity, not even inputs and outputs. In the ZX calculus, it doesn't even matter whether you think of inputs or outputs. You can always twist the legs around, and as long as they remain attached to the spiders, they always do the same thing, because spiders satisfy the following rules. So there's that, but there's also that you can twist legs around. So if I have a spider that has 2 legs in and 2 legs out, it's the same as having a, in fact, let me write it that. So we should have been a bit less boisterous about it. If I have a leg below, that's the same as taking a leg above, so an output leg, and twisting it down. And vice versa, if I have an extra leg in output, it's the same as taking a leg in input and twisting it out. But these are not rules that I have to impose. These are all rules that I can prove. They're all derived. Because all I have to say really is observe that if I can remove the spiders, then I can bend the legs around, and maybe I can also remove them in the caps. And I can remove them in the cups. So those are all good, those are all valid. And now I can say, okay, what is let's say this spider here with some angle. I unfuse it, so unfuse, and I get this spider here, and then I refuse it again. In fact, I make the snake here, snake, which is also fusion, but then I fuse the top one, and I am left with a spider that has 1 extra input leg that gets bent out. Something like that. So you have this leg and you say, okay, I turn my leg into a pair of a cup and a cap, so it's like a snake. They're just a bands of wire, really. That's what the left says. They're all just wires that you can bend around. If there are no angles, that all works. And then you sort of unfuse and refuse, and the leg has changed order. So you don't have to think about it. This is not something you have to do. It's kind of expected that when you manipulate these diagrams, you automatically remember that legs can be bent in and out. As long as they're attached to the right end of the full diagram, inside you can bend them as convenient. So going back to the C naught, can I prove that this is a C naught? Of course I can. So I'm going to apply it to 2 inputs, A and B. And remember that I encode my bits as multiples of pi. So 0 is 0 and 1 is pi. That's just because I want to work with angles. It's easier. And I apply copy and XOR. Now, first rule, I copy the state at the top. Actually, first rule, I fuse the state at the bottom into the XOR, and I get A pi here, gets copied. 1 leg will have this gate applied to it, the other leg has nothing. Then I copy true, and I get 1 copy at the top. And at the bottom, I get A pi, B pi, and now this is A pi at the top, and A XOR B pi at the bottom, and this is the control knot. This is what a control knot does. If A is 0, then B gets through unchanged. If A is 1, then B B pi becomes B plus pi, so B becomes not B. Okay, so this is the CNOT gate. This is what the CNOT gate does. And I can prove it by just applying two rules, really. I can fuse, I can copy, and I can fuse again. And this is now a composite gate, which has an interesting behavior that I prove just by using effectively fusion and copying of states. I have some simple rules that prove some more complicated ones. And now for the same, I want to prove that if I start in a quantum circuit that has 1 qubit in the plus state and 1 qubit in the 0 state, and I apply a CNOT to these two states, what happens? Well, I fuse one of them, and I get something like this. I fuse the second one, and I get something like this. Then I remove the empty spider with one leg in, one leg out, so only two legs, and I get something like this. And then I remove the other one, which is also empty, and I get cup. So really, this up to normalization, of course, which I forgot. This is the cup. The cup is the Bell state. Is the state you prepare by applying a CNOT to an entangled control, if you will. And if I wanted to normalize things, just to remind you that these are unnormalized. So if you want to carry around normalization factors, I'm going to write them in a different color, just to remember that I don't really care about them right now, but for your bookkeeping, then remember this spider was √2 times plus. Technically, this spider was not really 0, but it was √2 times 0 for convenience. And then I carry the spiders around, the scalar around 1/2, 1/2, 1/2, 1/2, something like that. So I get, technically I'll have to, actually the CNOT, sorry, had a √2 to it to do the normalization. There you go. That's correct. So I don't want to know about these scalars. The scalars are kind of annoying, and I don't need them in the calculations in the end. So nobody carries them around. In fact, there is work dedicated to writing the ZX calculus without scalars. And the entire point of all this work was to prove that you can reinsert the scalars at the end without imagining that this is quantum. Because of course, if you imagine that these are linear maps or you're working in quantum theory, then obviously you can always renormalize. But there is also work to prove that you can just diagrammatically ignore the scalars and reinsert them at the end. So this is, even just syntactically, it is a sound thing to do. So I'm going to disregard the scalars entirely and just, I'll keep this slide, but I'll remove the scalars. So that's it for today. I think we can take a breather, and I will continue tomorrow, where there's going to be a couple of things about spiders again, and then I'm going to go to relativity and probabilities, and we're going to redo teleportation and maybe another one or two of the protocols, but this time doing it right. Not writing boxes with skulls and set faces in them, but actually writing boxes that show us what the error is, and then correcting the error that we find. So for today, that's good.
Afternoon lecture at 2, but we are in that room a little bit early.
A little bit earlier, correct.
Formally, if you come at 1:30, we'll be there.
Correct.
Thank you so much.
Thank you all. Hope help yourselves to some donuts if you haven't already. I will. Let me save this.